In this talk, we will discuss some properties of posets arising from unitary spaces. I would like to thank the organizers of this Congress for giving me the opportunity of giving this talk. So I will begin with some preliminaries on poset and simplicial complexes. Suppose that X is a finite poset, then K of X is its ordered complex, and recall that the vertex X of this simplicial complex is just the underlying set of X, and the simplices are the non-empty chains of X. So we can study the topological properties of X by means of the geometric realization of this simplicial complex. So in particular, if G is a group acting on X such that X is a G poset, then K of X is a G complex and the geometric realization is a G space. So for example, take V to be an n-dimensional vector space over a finite field F of characteristic P, and take P of V to be the poset of all non-zero subspaces of V. Then note that this poset is contractible because its ordered complex is a cone in the vertex B, which is a maximum of this poset. So maybe it's more interesting to study the posets of proper non-zero subspaces of V, that is supposed obtained by P of V and removing V. So a classical theorem of Solomon-Tietz states that this poset is homotopy equivalent to a wedge of spheres of dimension n-2, which is the dimension of this simplicial complex. So this is homotopy equivalent to a wedge of spheres of the maximal possible dimensions, and this is the number of spheres. So from this, it is easy to compute the Euler characteristic of this poset, which is given by this number. And in fact, we have that this poset is homotopically Cohen-Macaulay. So let me now recall the definition of Cohen-Macaulay. We said that a poset X is homotopically Cohen-Macaulay if the following conditions hold. First, X is spherical, which means that it is a homotopy equivalent to a wedge of spheres of the maximal possible dimension, which is the dimension of X. And moreover, all the links in X are also spherical. And that means the following. If we take two elements, X and X prime, so that S is at most X prime in X, we look to the subposets of elements strictly below X prime, strictly above X, and the intersection between these two, which is the interval between these two elements, then these three posets are spherical of the correct dimension. And the correct dimensions are given by the following numbers, where h of X here denotes the height of the element. So in our example, we have by the Solomon-Tietz theorem that P of V is spherical. Okay. Now, if we take two subspaces here as contained in T, then and we look for these links, then the elements strictly below T is just the same poset of proper non-zero subspaces of T. The elements above S is just the proper non-zero subspaces of V over S. And the interval is analogously the proper non-zero subspaces of D over S. And all of these are spherical again by the Solomon-Tietz theorem. So this poset is Cohen-Macaulay. Now, we also have a group action here. And this is given by the group of all linear isomorphisms of V, which is just a linear group of dimension n over the field F. Okay? So she permutes transitively the set of k-dimensional subspaces of V for each k between 0 and n. Okay, recall n is a dimension of V. And moreover, she is transitive on the maximal chains of this poset. So in conclusion, we see that this poset is very well behaved. It is very homogeneous. It has very nice homotopical properties. So now we will be interested in studying posets arising from spaces with a form, and in our case, with a Hermitian form. So this means the following. We are going to add a form C such that V is a unitary space. That is, there exists an involution of the field, of the ground field, such that this is not identity, okay? And moreover, this form is not symmetric, but it is symmetric up to applying theta. Okay, so this relation holds. For the linearity, we asked to be linear in the first variable, but not in the second one. Okay? But we can deduce some properties by using this relation, this symmetric relation. And now we are going to ask for the radical of this form to be 0. And this means that the only vector that when we apply C of this vector V against every vector W is 0. Okay, the only vector that satisfies this condition for every vector W is the vector 0. Okay, so this is a 0 subspace. So in that case, we say that V is a unitary space and that C is the Hermitian form. So there is a very nice property that unitary spaces are unique. That is, if we have another unitary space over the same field with the same dimension, W, then these two spaces are isometric, which means that there exists an isomorphism between V and W that preserves the forms, that sends C to C prime. And now what is the condition for these unitary spaces exist? So unitary spaces over F exist if and only if the size of V is a square, like this. And moreover, in that case, theta is just the involution that takes an element to the Q. Okay, so that is fixed subfield here if FQ, and F is the finite field of Q to the square elements. Moreover, in that case, we can define an explicit Hermitian form, which is given in the canonical basis, in this case, in this vector space, as follows. So we'd say the inner, the form between two vectors V and W is just the sum and the product of the coordinates and the coordinates of W is at the Q power. And this isometry, and this form is unique up to isometry. In particular, we see that orthonormal bases exist. Now, we define the non-degenerate subspaces corresponding to this form. So suppose now that V is a unitary space and we take S to be a subspace, then the orthogonal complement is just a vector that the form is 0 against every vector of S. And there is a nice properties with this orthogonal complement. The dimension of this orthogonal complement is just the codimension of S. And we say that S is non-degenerate if and only if it intersects trivially to its complements. So by definition, note that V is non-degenerate because its complement is just a radical, and we ask the radical to be 0 by definition of a unitary space. So we are interested in studying the following posets. The poset SV of all non-zero and non-degenerate subspaces of V. Now, note that by this observation, V is contained here. It's an element of this poset. So this poset has a maximum, and again, it is contractible. So we are also interested in studying the posets of all proper and non-zero non-degenerate subspaces of V. Okay, so which properties do we have in this poset? For example, do we have a Cohen-Macaulay property or spherical condition? Do we have an homogeneous behavior as in the poset of all proper non-zero subspaces? Do we have a group action here? Can we compute its Euler characteristic? We will see how to answer some of these questions. For example, one of the key properties of the poset of all proper non-zero subspaces is that after adding the zero subspace here, then we get a lattice. And in fact, it can be shown that this poset here is a Tietz building. That is, its order complex, it's a Tietz building. The first issue that we find here is that this poset is not a lattice, because the intersection between two non-degenerate subspaces might be non-degenerate. Okay, so let's study now the group action here. Now we are going to consider the group that preserves the form, and this is a general unitary group. That is, this is the group of isometries of our unitary space. In the case that V is just this canonical space, then this group we also denoted by GU in dimension n of Q. I know that we are not using q at the square here. We are just using q, but other authors might use q at the square here to emphasize that this is the ground field. So since this group preserves the form, in particular, it will preserve the non-degenerate subspaces. So it acts on these posets. And here we have a fundamental tool, which is Witt's lemma. Witt's lemma states that if we have two subspaces, n subspaces of our unitary space B, and we have an isometry between S and T, which means that this an isomorphism between these two subspaces, which preserves the form. Here, the form is the form of B, which is a Hermitian form restricted to S and T. Then this isometry extends to an isometry of B. And this is very nice because basically we see now that by Witt's lemma, this group is transitive on the set of n-dimensional non-degenerate subspaces of B. So this is very similar to the case of the general linear group acting on the poset of all non-zero and proper subspaces of B. So with this analogy, we get a similar conclusion with the group action. So this poset, this new poset S of B, is very homogeneous because of this action, thanks to Witt's lemma. So suppose that you denote by Sm of n the number of non-degenerate subspaces of dimension m inside an n-dimensional unitary space B. Define these numbers. Tilde 0 of q is just 1 by definition, and for n at least 1, we define this number to be just the Euler characteristic of this poset here. It is just the Euler characteristic of S of V in the case that V is n-dimensional unitary space over f q at the square. Okay, so now also denote by Gn of q the size of this unitary group. So we can compute the Euler characteristic by this inductive formula. So note that here that we have here the sizes of these unitary groups, which can be computed. And inductively, we have the Euler characteristic here, the reduced Euler characteristic of the poset of proper non-degenerate subspaces of a unitary group of of a unitary space of dimension m, and m here is less than n. So in particular, if we group all together, we can find the following relation that all the sum here is 0. If this term, we put this term here in the sum as the nth term. And this is a polynomial in Q. And it will be very interesting to study the properties of this polynomial. Please note that this polynomial is more complicated than the polynomial of the Euler characteristic of the poset of proper and non-zero subspaces of B. Okay, so now let's study a bit the homology of this poset. First, note that this poset is included in the poset of proper non-zero subspaces of B, and both have dimension n-2. So in particular, we have an inclusion in the top degree homology group, and it can be shown, in fact, that this homology group is non-zero. Okay, we know that this one is non-zero because it is non-trivial wedge of spheres by the Solomon's theorem, but it can also be shown that this one is non-zero because basically we can construct a cycle here that in fact lives in this homology group. So this can be shown. Okay. So, but what about the Combinatorial property of this poset? Or do we have an sphericity condition here or something like that? So we want to study the links, okay? It's because the Combinatorial property involves links and spherical links. So the links here are easy to describe. If we fix an element of the posets, then the elements strictly below them is just the same poset of proper non-degenerate subspaces. And the element strictly above T is, again, the posets of proper non-zero non-degenerate subspaces of B over T. And of course, you can imagine how is the interval. So a theorem of de Villers, Gramlich, and Muchelker states that if this bound holds, then this poset is Cohen-Macaulay. So that means that all these links and the intervals are spherical of the right dimension. However, some experiments show that it fails if this found does not hold. That is, for example, if you take q equal 2 and n equal 4, then we should have here the dimension of this guy is 2 as a simple cell complex. So we expect this to be homotopy equivalent to a wedge of spheres of dimension 2. But the first homology group here is non-zero. Okay, so it cannot be homotopy equivalent to a wedge of spheres of dimension 2. So it is not spherical. Okay. Another computation communicated by Volman-Berger states that if we take q equal 3 and n equal 4, then again in the first homology group here we find torsion. We find a cyclic group of order 3. So again, this is not zero, and moreover we have torsion here. Okay, we have 3 torsion here. So moreover, it cannot be a wedge of spheres of any dimension, nor even of different dimensions, because we have torsion. So it cannot be a wedge of spheres. So we conclude that, in particular, this poset cannot be a building. It is not a column, it is not a wedge of spheres in general. Okay, so now let's pass to another poset complex related with these unitary spaces, and this is a frame complex. So again, fix B to be an n-dimensional unitary space, and we are going to take the following simple cell complex f of B. The vertices are the one-dimensional non-degenerate spaces of B, and the simplices are sets of pairwise orthogonal one-dimensional non-degenerate spaces of B. So these are stuff like this: B1, B2, up to BK. For example, these are the simplices, and these B sub I are one-dimensional non-degenerate subspaces of B, which are pairwise orthogonal. Okay, these are the simplices. So a simplex here of size K is termed also a partial or K frame of B. Okay. So we can also regard this simple cell complex as a poset. We see the underlying set of this poset is just the set of simplices, and the order is given by the inclusion between the simplices. So now we are interested in studying the properties of this simple cell complex, the combinatorial and homotopical properties of this complex. Sorry. So the first property that we find is that if we regard this as a poset and we add a maximum and a minimum here, then it is a lattice now. Because now the meet is just the intersection between simplices, right? Moreover, this complex has dimension n-1 because a maximal simplex here is just a full frame that is set like this, an orthogonal decomposition of your unitary space in n orthogonal one-dimensional non-degenerate subspaces. However, we find that this complex collapses to a subcomplex of dimension n-2. And that's mainly because if we have an n-1 frame, that is a simplex of dimension n-2, then this is contained in a unique frame, right? Because the only frame contained in this one is the frame obtained by adding the orthogonal complement here, which is unique of dimension 1. Because here we have dimension n-1, if we take the span of these subspaces. So the orthogonal complement has dimension 1. It is a unique thing that we can add here. So we have this collapsible faces in our simple cell complex. So it collapses to a subcomplex of dimension n-2. Moreover, now the group of isometries, the general unitary group, acts transitively on the set of K frames. Okay, it's because basically by Witt's lemma again. So now from this, it is easy to compute the Euler characteristic. Now denote the set of K frames by Fk of B. So the transitive action here allows us to describe easily the stabilizer of this action. And hence we can compute easily the size of this set. So now to compute the order characteristic of this simplicial complex, we need to take the alternating sum of the sizes of these sets. And by this formula here, we obtain this polynomial in Q again. So it also would be very interesting to study the combinatorial properties and the algebraic properties of this polynomial. Okay, so what about now the homotopical properties of this poset? So if we regard this as a poset, okay, now we see that every n-1 frame is contained in a unique frame, so it's a unique maximal element. So we can remove all of them and obtain a homotopy equivalence of poset. Okay, so we regard this as a poset now, and we erase the n-1 row. Okay, and we obtain an homotopy equivalence sub poset. Okay. Now the links again are easy to describe. If we look in the upper link, we obtain the orthogonal complements, and if we look in the lower link here, we obtain a wedge of spheres of the correct dimension. So we may also look for the Cohen-Macaulay property here, but we don't know what happened with that yet. For example, we know that if n is at most q times q minus 1, strictly less, sorry, then we have non-zero homology in the n-2 degree, which is the top degree here, okay, because this has dimension n-2. However, some computations show that we also have non-zero homology group of degree less than the top degree. So this is also non-zero, and we have free non-zero homology in degrees k, where k is not equal to n modulo 2. So in particular, we have non-zero homology in other degrees than n-2, when this bound here does not hold. That is, we have the other bound. So in particular, we also see here that these posets are not spherical in general. Okay, they are not spherical, they are not Cohen-Macaulay. And it is, of course, it's not homotopy a wedge of spheres of dimension n-2. So now to end this talk, let me give you one insight or one motivation for studying these posets. And that's related with the Quillen conjecture. So there is an open question, whenever it is always true that we have non-zero homology in this top degree. So now, fix P a prime number and G a finite group, okay? And now consider the poset SPG of all non-trivial P subgroups of G with the order given by the inclusion of the subgroups. So we have an action here of G on this poset, which is given by the conjugation between the subgroups. And we take SPG to the G to be the fixed points of this conjugation action. That is the non-trivial and normal P subgroups of G. So the Quillen conjecture states that if this poset is acyclic over the rational number, that is, if it has zero free homology, then we have a fixed point by this action. The most advanced result on this conjecture, which remains open, is the Ashbacher-Smith theorem, which states that if P is an odd prime, then this conjecture holds for G, except perhaps if she contains this projective special unitary group, subject to some conditions between P and Q, and such that the n-2 homology group of this poset is 0. So if we can show this question here, we can answer positively this question here, we can then finish the proof of Quillen's conjecture for all primes. And one idea here is to try to construct a non-zero cycle here by using the non-zero cycles of this other poset here, that we know here that we have non-zero homology in dimension n-2. So we can try to construct a cycle here by using the cycle here. That's all. Thank you very much.